All right, thank you so much for coming to today's webinar by Yale, KCITY. I'm going to post some information about the KCITY in the chat box. You're welcome to stop by KCITY website to review other presentations that we have and also the presentations that we are going to provide in the next few weeks. I'm extremely pleased to introduce Professor David Kwabi, who is actually a colleague in my department, the Department of Chemical and Environmental Engineering. David graduated from Princeton Mechanical Engineering, BS, and then he went to get his PhD from MIT, and then did postdoctoral training at Harvard. Hey, your pedagogy is amazing, David. And then he started his career at University of Michigan. He was doing extremely interesting work. He's been working on this grid scale energy storage systems that uses like redox flow batteries and CO2 capture. And then when we were looking at his research, we were very, very impressed. He has this continuation of research on this energy and resource efficient electrochemical systems to address decarbonization and climate change. And he was so good, so Yale recruited him recently to join our team. He has been so humble. I asked him to give me his bio. He deleted all his award, but he has many awards, including ASME Rising Star Award, which is not surprising, and prestigious National Science Foundation Career Award. All right. Hey, David, I will let you go. Thank you so much again for your presentation. Yeah, here you go.
Great. Thank you very much, Jihong, for that very generous introduction, and to you all for waking up early to hear about some of my research. So I'm going to start by going through a little bit of motivation of sort of why we do what we do in my group here at Yale. And it's really dependent or inspired by the fact that a lot of the way we use energy today is coupled to fossil fuels and CO2 emissions. So the plot I'm showing here is shows sort of historical and projected trends in terms of global primary energy consumption. It's one that many of us might be familiar with. And it kind of communicates two key points, at least to me. The first is that renewables, as you can see, are poised to comprise a significant fraction of energy use through the middle of the 21st century, which is good news. But the other thing you realize by looking at this plot is that even by the middle of the 21st century, so by 2050, if you count up the amount of energy we are burning or we are consuming, represented by coal, oil, and natural gas, we're still going to be burning a significant amount of fossil fuels and emitting a lot of CO2. So given this sort of business as usual trajectory, the expectation is that we will not hit our climate goals of reaching net zero, so to speak, by 2050. So to hit net zero, we have to be using significantly more clean energy, mainly in the form of renewables, more than is projected at the current pace. So there's clearly an incumbent task on us as a society to more rapidly shift away from fossil fuel energy, or actually to start taking seriously this idea of removing CO2 from the atmosphere in order to achieve our climate goals, and particularly the goal of being staying below 2 degrees C of warming relative to the pre-industrial era. There are a number of ways of going about these tasks of shifting to alternative energy and also using or enacting carbon capture. In my group, we're particularly interested in accomplishing these goals with electrochemical systems. So just to give you a brief overview of my presentation today, I'm going to be going over our work on developing energy storing organic molecules for use in redox flow batteries. And then I'm going to talk to you about how we're thinking about using ceramic membranes as key components in these systems to enable high voltage, low cost configurations. And then I'll say a few words about how we are taking some of the insights we're learning from our work on electrochemical energy storage and applying it to this problem of carbon capture, and more generally, chemical separation, so what we call resource recovery. So the idea is we're learning a lot from our work in energy storage, and we're applying it to various contexts, or other contexts that are relevant to climate sustainability or industry more generally. But first, let me say a few words about flow batteries. For those of you who might not be familiar with these systems, they're very different from the enclosed lithium-ion batteries that you might have in your cell phone or your laptop computer. You can think of a flow battery as essentially a rechargeable fuel cell. So instead of having hydrogen and oxygen gas that are routed into an electrochemical cell, you actually have two tanks of liquid containing liquid reservoirs that hold molecules or ions that can store charge. And flow battery works by essentially flowing these electrolytes. You have a negative electrolyte and a positive electrolyte into an electrochemical cell where you have redox reactions that either store or deliver electricity. And of course, the difference between the voltage on the negative and positive electrolyte reservoirs is what defines the voltage of your battery in this case. What's nice about this architecture is that the size of your electrochemical cell stack, which I'm highlighting here, can be modified independent of the size of the reservoirs. And so you have a way of changing the power capacity of your system without changing the energy capacity or vice versa. And so this is a very sort of flexible design characteristic which makes flow batteries appropriate for long duration or grid energy storage, particularly of renewable electricity. So the state-of-the-art chemistry that's used in these systems is based on vanadium. Vanadium, however, is inabundant in the Earth's crust. It's a fairly rare metal, and so it's quite expensive, right? The goal, one of the longstanding goals in the community, is to try to replace vanadium with molecules that would be a lot cheaper. And particularly, we've been interested in organic molecules as substitutes for vanadium in these systems. I'm showing a few examples of charge storing organic molecules that can be found in nature, for example, in fruits and vegetables. They're used in commercial dyes in the food and textile industry, and even in cosmetic products. So something like acne medication contains a molecule that's redox active and that can be used in principle with some modification in these sorts of flow batteries. This bottom right picture shows an image of anthracene or coal tar, really, which contains a lot of anthracene, and anthracene can in principle be oxidized to quinone, which can then be used or modified for use in these flow batteries. And so the idea is to take these materials, which are going to be a lot more earth abundant and presumably a lot lower cost than vanadium, and deploy them in flow cells. So this is one of the things that we do in my group is we take these molecules, we modify them, and then we test them in flow batteries to figure out how they perform the way they do and what to do to modify or increase their performance. So one of the ways we do this is with spectroscopy. So we have our flow cells, for example, and we have two electrolytes on either side. We have inline or real-time monitoring of the chemical composition of the electrolyte while the flow battery is cycling. And this gives us tremendous insight into what's going on as we are charging and discharging the battery. So on the right, I'm showing a trace of the charge accumulated in the battery as a function of time. And then up here, I'm actually showing the real-time spectroscopic data from the electrolyte. So we're able to gather a lot of data about what's going on in these electrolytes. And one of our longstanding goals is to use that data to figure out exactly why we're seeing degradation, for example, of some of these organic molecules, and to use that information to then design more resilient organic molecules. Okay. So using this spectroscopic data, we go through a lot of spectral analysis. So those of you who might be familiar with ultraviolet visible spectroscopy might know that in general, the absorbance that one measures is a product of the concentration of species that are present and molar absorptivity. Now, because we are measuring absorbance at a series of wavelengths and through time, we actually end up with what you could call an absorbance data matrix, where each row represents a point in time and each column represents absorbance at a given wavelength. And so we can, in principle, take this big matrix and decompose it into a concentration matrix, where N here is the number of components that are present in our electrolyte. And then we have T, which is, of course, time. So we have a concentration matrix, and we have a molar absorptivity matrix, which represents the pure spectra of all the components that are present in our mixture, how they how they evolve in time. So the big takeaway here is that by taking this spectroscopic data, we can look at concentrations of various species over time, and this gives us a way of inferring or understanding the kinetics of degradation of these organic molecules. So I'll give a sort of a brief highlight, sort of a case study of how we've used these techniques and other techniques combined to make some progress in designing better molecules. So this is one example of a molecule that we've studied. It's called an azobenzene. It's the same molecular family as one of the dyes I showed in one of the earlier slides. We took this molecule, we put it in a flow battery, and we discovered that it actually undergoes very rapid capacity fade over time. So this is, if you look at the x-axis here, this is on the order of a day or two. We lose almost all of our capacity in our battery as we cycle it. Now, by applying our spectroscopic analysis to the electrolyte as it's undergoing cycling, we found that it's in the reduced form. So after we've reduced it, we end up with this form. We actually end up with a breakage, or if you like, a cleavage of this nitrogen-nitrogen bond. And we end up with two fragments that are not active in our battery. So the nitrogen-nitrogen bond is sort of weak, it cleaves, and then we end up with capacity decay. And so we hypothesized that by adding an extra bond between these two arrow groups, we would stabilize the molecule against this cleavage process. And so we used density functional theory or atomistic calculations to calculate the rate of degradation, or the free energy of degradation for this new molecule. This is a benzosynolene, and this is an azobenzene. So for the benzosynolene, we looked at the free energy of degradation predicted by atomistic calculations, and we found that it was a lot less negative, so a lot less likely to happen thermodynamically. We were very encouraged by these results, and we synthesized this new scaffold and found that our degradation rate was tremendously slowed. So we are going from losing about 80+% of our capacity in about a day to losing about 0.1% on the order of 0.1, 0.3% per day with this new scaffold, which was very encouraging. So this sort of gives you a sense of how our workflow operates, where we can take one molecule, we can understand how it degrades, and using that information, we can design more resilient systems. There are a number of other examples I can show where we've gone through this sort of process. One example we're particularly proud of has to do with these molecules called quinoxalins. So quinoxalins are very low-cost nitrogen-containing molecules that are somewhat easy to synthesize from very low-cost precursors. This quinoxalin, as you can see here, is commercially available. We found that it actually degrades at a fairly high rate. So again, if you look at the x-axis, on the order of a day or two, we're losing most of our capacity. By applying the same spectroscopic techniques that I just introduced, understanding the rate of the mechanism of degradation, we're able to select a slightly chemically modified version of this molecule with a carboxylic acid in a different position. So you can see here, carboxylic acid on this molecule is in the 6th position. Here it's in the 2 position. And we're getting rid of the 2 methyl groups that used to be here. Okay, so it's a fairly subtle chemical modification to the structure of the molecule. But we found that making this modification actually ended up boosting our lifetime by a significant fraction. So we're again going from losing most of our capacity in 2 days to not actually being statistically able to measure a rate of capacity fade because it's so slow. We think it's on the order of a couple % a year, extrapolating from some data we gathered over the course of weeks. So again, the takeaway is that we can really get significantly improved chemical stability of these organic molecules through adjusting, making some subtle but targeted functional group adjustments. So kind of zooming out and thinking about how these molecules might be industrially relevant, the idea is that if we have a molecule or pair of molecules in negative and positive electrolyte that are both robust chemically, but also inexpensive to procure and synthesize, this then gives us the opportunity to start thinking seriously about scale-up of these systems. So just to give you a sense for what that might look like, there are a number of startup companies around the world that are pursuing flow battery technologies. Most of them are using the more expensive vanadium chemistry I mentioned earlier, but there's a potential to use organic molecules and get a much lower energy cost or electricity costs overall. So Lockheed Martin was one of the early companies to commercialize or put up pilot plants, pilot flow battery plants. And the biggest flow battery plant I'm aware of is a 800 megawatt hour plant in China, which again operates on the vanadium chemistry. So these batteries have tremendous potential. They could be used, like I said, for grid energy storage. They could also be used for arbitrage on the grid. And they can also be used in principle for backup power for critical industries. So for example, hospitals that cannot afford to lose power for an extended period of time. And lately, of course, with the surge in AI and the realization that these data centers that power AI actually need a lot of energy, they in principle could be used as additional or auxiliary power for data centers as well. So I'll switch gears and talk a little bit now about our work on ceramic ion conductors in flow batteries.
Can I ask a question, David?
Yes, absolutely.
Yeah, compared to like industry benchmark batteries, I mean, we hear a lot about like fires and things like that.
Mm-hmm.
Can you comment a little bit more about the stability of redox flow batteries?
Yeah, so the nice thing about flow batteries is that these are aqueous flow batteries. So the electrolytes here are water-based. And so we actually don't have the same flammability concern that as we would with a lithium-ion battery system. The advantage actually turns out is that it means you can actually stack or put these batteries a lot close together and for a given footprint or area of your plant. Whereas with lithium-ion batteries, because of fire concerns, you have to space them out quite far apart from each other, or each battery from one battery from another, essentially. And so a modern flow battery plant would actually have the same footprint in terms of watt hours per meter squared as a lithium-ion battery, even though lithium-ion batteries are more energy dense. So I
That
hope that
sounds
helped.
interesting. How small it can it be?
That's a good question. It depends on the application. The battery plant I'm showing here is about the size of a city block. In the lab, we're using batteries on the order of like 5 square centimeter electrode area, which is good enough for just prototyping, but won't power much more than a light bulb also for
Right.
a few
I mean,
hours.
in the future, can we expect the flow batteries in a size of like Tesla batteries that you have in a home, like receiving solar power and store for household usage?
That's possible. So any sort of stationary storage would be appropriate. Obviously, we cannot put these in electric vehicles, for example, but These would be ideal for residential use. In principle, if you have a big enough basement and so on. They could also be useful at the municipal level or even for microgrids as well, or zooming out to larger, like a town or a city or something like that.
Sounds wonderful. Thank you.
Great. So I've mentioned quite a bit about designing organic molecules for use in flow batteries and essentially protecting against degradation, which leads to capacity fade. Another route for capacity loss in these batteries is crossover of active molecules from one electrolyte to the other. So we ideally want the two electrolytes to stay separate and only have a single current carrying ion go between both sides. But in reality, it's possible for there to be crossover from one electrolyte to another, which we don't, which you don't want to avoid. So for the past 3 or 4 years, we've been playing with this idea of, rather than using typical sort of polymer membranes in these flow batteries, of using ceramic ion conductors. And what's attractive about them is that they would bring about perfect separation between the negative and the positive electrolyte, because these are fully dense, hard ceramic materials that only permit, for example, a sodium or a lithium to cross from one side to the other. In principle, we would have no crossover-induced capacity fade. So we've been playing for a while now, or exploring this concept with the so-called sodium superionic conductor, or NaSiCon. NaSiCon is a ceramic material. It's an oxide of sodium zirconium phosphate and sodium zirconium silicate. So it's a solid solution between these two oxides, essentially. And the structure of NaSiCon is such that it's a three-dimensional lattice or network in which we can have sodium diffuse in 3D. So the structure of the lattice is essentially zirconium and silicon, zirconium oxide and silicon oxide, octahedra and tetrahedra respectively. But because we have this 3D diffusion of sodium in the structure, we're able to get a very high conductivity. And as a result, these materials are actively being studied for use in, for example, sodium metal batteries. But we believe that they could be appropriate for use in flow batteries as well. So one of the things we discovered fairly early on in our work here is that the conventional way of synthesizing these NaSiCon membranes gives rise to a very heterogeneous microstructure. So the traditional way one synthesizes NaSiCon is you take powders of sodium carbonate, zirconium oxide, and then phosphate. You mix them together, you heat them at about 1600 degrees C. That then results in a NaSiCon powder, which you can then hot press at high temperature, and you end up with a pellet. So you have a pellet of your NaSiCon material, which you can then put into a flow battery. And it turns out these materials are indeed excellent at withstanding, preventing crossover. But we found out, looking at the microstructure of these materials, that they're extremely heterogeneous. So you have regions that have a NaSiCon grain, so the crystalline material, but you also have secondary phases. So zirconium oxide is one example of a secondary phase, and you also have amorphous phases in the microstructure as well. So one of the questions that we set out to ask in going about this research is, how do these different phases respond to the aqueous electrolyte while they're actually being cycled in the flow battery? The research is actually being done as part of a Department of Energy funded Energy Frontier Research Center, or EFRC, that's called Mechanochemical Understanding of Solid Ion Conductors, or MUSIC. And the overall goal of MUSIC is to understand how ceramic or solid ion conductors such as NaSiCon respond chemically and also sort of mechanically, how their mechanical properties change in the presence of aqueous electrolytes, and also in other contexts. So this EFRC center is full of other researchers. It's a consortium of about 14 or 15 PIs from around the country that I collaborate with, who are helping to answer some of these questions. So one of the things we did was to team up with our collaborator at Oak Ridge National Lab to do a deep dive into this microstructure that I just mentioned. So these different phases, this nasicon, crystalline nasicon phase, zirconium oxide, and a glassy phase. So my collaborator Miafang used high-resolution electron microscopy to sort of map out the crystal structure of both the nasicon and the zirconium oxide crystalline phases. And then she used what's called a 3D cryogenic slice and view focused ion beam technique, where essentially they mill out very thin sections of material and image that material with electron microscopy. She used that technique to essentially reconstruct or put together a 3D reconstruction of how the various phases are oriented. Right? So we can see here that there's about 90% of the crystalline phase, about 7% of the amorphous phase, and about 2% of the zirconium oxide phase in the sample. And what's neat about this slice and view technique is that you can actually really nicely see how interconnected all these phases are within the microstructure of nasicon that's made by using this conventional technique. So the next thing we discovered is that the glassy phase is actually a very different chemical composition than the crystalline phase. So it actually contains a shell that is a sodium deficient version of nasicon. And then it has a core, which is a sodium phosphate, which looks very much like sodium phosphate. And you can actually see how this core shell microstructure is sort of arranged on the right plot here. And so both of these materials are actually poor ion conductors. And so we want to avoid forming them because they would essentially lead to degradation in performance of our membrane. One of the nice things about electron microscopy is that you can also see some of the degradation that occurs in very exquisite detail. So this is an image or a series of images showing the glassy phase of nasicon upon immersion in aqueous electrolyte actually dissolving over time. So we start off on the far left with our pristine material, and then over time we see that the region where the glassy phase is present actually erodes completely. So we have dissolution of this glassy phase. We know that it's already a poor ion conductor. And we know all of this from very high resolution imaging of the microstructure. So what we then did was to substitute this conventional process for making nasicon, which results in degradation of the glassy phase, with another technique where our precursors are not mixed as solid powders, but actually dissolved in solution, in what we call a solution-assisted synthesis of nasicon. So we've essentially modified the process for making nasicon in an attempt to mitigate the presence of the glassy phase on the secondary zirconium oxide phase. And as you can see on the bottom left here, that this new technique was quite successful at doing both. And we found that upon immersion in a variety of different electrolytes, we actually saw very good stability. So we had excellent stability of this new nasicon formulation owing to this new technique for fabricating it. And this is more TEM or electron microscopy data showing that, again, upon immersion in various electrolytes, or in this case, in 0.1 molar KCl, we have fairly robust stability. So what we're now doing with these membranes is putting them into redox flow batteries. And one of the, of course, goals is to prevent crossover, like I said, and bring about better capacity retention than we would have with a conventional polymer membrane. But the other advantage we've realized that these membranes carry is that because they are perfectly selective, in this case, for sodium ions going from the negative to the positive electrolyte, we can actually have two different pH environments on either side of the battery. So on one side, we can have an alkaline electrolyte, for example. On another side, we can have something close to neutral. And so this really opens up the space for combinations of electrolytes. We can have a negative and positive electrolyte in a way that we're limited with a conventional polymer membrane, where we have to have a single pH because protons and hydroxides can easily cross over to these membranes. So the result is that we're able to put together novel combinations of or novel flow battery configurations that in principle could lead to low cost. So we have a negative electrolyte, in this case, that's based on a very low-cost chromium complex, and a positive electrolyte based on manganese. These are different pHs, but we're able to cycle them, or cycle these electrolytes, because we have this Nasicon membrane preventing the equalization of the pH gradient. There were other applications that these Nasicon membranes can be used in. One of them is solid-state lithium or sodium metal batteries. I should mention that the sodium in Nasicon can actually be replaced with a variety of different ions. So you can replace the sodium with lithium, you can replace it with silver, ammonium, etc. And so that brings about the possibility for a variety of different applications with these ceramic materials or ceramic membranes. So one of them could be desalination, for example, of seawater or various types of brines that have high sodium content. As I said, we can use these in solid-state batteries for grid energy storage or even for electric vehicles, for example. And then, in principle, if we replace the sodium with ammonium Nasicon, then we can now use this to extract ammonium from wastewater, just as an example, to be used as fertilizer. So these are, again, some possible applications or ways we can extend how we're using these materials into more industry-relevant contexts. Okay. And then lastly, I wanted to touch on some of our work on carbon capture. And a lot of it is motivated by the fact that many of the molecules, of the organic molecules that we use for energy storage are actually capable of what we call proton-coupled electron transfer. So upon reduction of the molecule, you actually pick up not just 2 electrons, but also 2 protons from water. And so that means going from left to right that you are de-acidifying or making your electrolyte alkaline if you're doing this in a bulk electrolytic type of configuration. So going from left to right, you can have an alkaline electrolyte. That alkaline electrolyte can capture CO2 from air, where it reacts to form a carbonate or bicarbonate. And then you can acidify the electrolyte by oxidizing the molecule. You release those 2 protons, and now you have CO2 that can then be sequestered or separated as a pure gas. So we're essentially using the sort of increased chemical stability, but also this extra potential of doing a pH swing to enact CO2 separation. Now, I won't get into the technical detail here, but we made a molecule based on this phenazine scaffold, which is soluble in water. We put it in something that looks like a flow battery. And now we're cycling it as we would a regular flow battery, but now we have CO2 in the headspace. We can monitor the absorption and release of that CO2 gas. So here's an example of some of the data we're able to generate. Current voltage, these are current and voltage traces from the electrochemical cell. You can see that as there's an increase in pH or alkalization of the electrolyte, there's the CO2 capture, so we have a dip in our partial pressure of CO2. And then when we oxidize the electrolyte, there's a decrease in pH and an increase in partial pressure of CO2 as we release that, as we release the inorganic carbon that was captured previously. So this is a proof of concept that got us very excited about the use of these systems for CO2 capture. But what we've become more interested in lately is this idea, not just of capturing CO2, let's say from flue gas or air, which turns out to be very challenging, but actually releasing CO2 from seawater. So, if you might know that we release about an order of 20 gigatons of CO2 per year into the atmosphere, the oceans actually absorb about 1/4 to 20% to 1/4 of the CO2 that we emit into the atmosphere annually. Now, that CO2 exists mostly as bicarbonate, but if you can reversibly acidify that seawater, you can turn it into CO2, you can capture that CO2, return the seawater to the ocean, and then you can use the ocean to then passively draw down more CO2 from atmosphere. And so capturing CO2, removing CO2 from seawater can be an indirect way of mitigating our atmospheric CO2 levels. So we've sought to take the molecules I just illustrated, so the ones capable of this pH swing process, and modify them in such a way that they can be used to enact a pH swing in seawater. So what I'm showing in the bottom left here is a system that we've developed that takes in a fixed amount of CO2 of seawater. Sorry. It then acidifies that seawater, pulls out the CO2 that comes out, and then alkalizes the seawater, and then it releases it to a different reservoir. And it does all this in an automated fashion, so all the flow paths are sort of coordinated with the operation of the electrochemical cell. So within the electrochemical cell, we have an electrode. So this is, we're now taking one of the molecules I just showed, and we are making it into a solid as opposed to liquid electrolyte, so that it doesn't leach into the seawater. And the idea is now, as we charge and discharge the electrode, we actually now have protons from seawater go in or out. So we have a reversible process. We've now been able to take our automated system and this electrode and demonstrate that over the course of several hours, you can get reliable acidification and alkalization of seawater and also CO2 removal. And we're currently in the process of optimizing the setup so we can end up with high separation rates and low energetic costs. This technology was largely developed during my time at the University of Michigan, and we're very fortunate to be able to license it to a startup company called Blue Ship Carbon, which was incorporated last year. It's raised about $1.5 million in pre-seed funding and is trying to bring this vision of seawater carbon removal at scale to reality, so to speak. And one of the things that Blue Ship is interested in is co-benefits. So in addition to generating CO2 that could be used, for example, as a feedstock for building materials, sustainable fuels, the beverage industry, and so on. They're also interested in using the pH swing that's generated in this process as a way of extracting critical minerals from various types of industrial wastes. So things like nickel, rare earth elements, and so on. So the hope is to use renewable electricity, seawater, and industrial waste as our inputs, with, of course, with the right sort of hardware in the middle here. And then we have rare earth elements, CO2 depleted seawater, and then some solid carbonates as the output. And I'll mention another potential application or use of the CO2 that's generated in this process would be for something like enhanced oil recovery, where the CO2 gas is injected to depths where there's oil being produced. And so the oil then comes up, it can be used for, essentially, the oil can then be captured and used in the fossil industry, but then the CO2 just stays buried at underground. So these are some of the potential applications or ways that some of our work in carbon capture could be extended. I'll mention very briefly that we're also interested in the possibility of triggering pH swings, not just with renewable electricity, but also with sunlight. So we've been working on this idea of using implementing photochemically active molecules in reactors for CO2 removal from seawater. So this molecule is a photoacid. When you shine light on it, a visible light, you end up releasing a proton, and that proton can react with bicarbonate in seawater and again release CO2. And then in the dark, you have the opposite process where your molecule is reprotonated. And so now you'd have alkaline CO2-free seawater that can go out into the ocean and capture CO2 from the atmosphere. This idea is actually a very similar idea is actually being pursued by a startup company that's not affiliated with my group, but it's nevertheless encouraging to see that some of these initiatives are sort of making headway in the real world. So Banyu Carbon is a startup that's trying to use photoacids to remove carbon from seawater in order to generate carbon credits. And then lastly, I wanted to mention one more area in terms of new directions for the group is we're hoping to go away from this conventional solid state synthesis where we have to heat materials to extremely high temperatures for extremely long times, and develop new ways of fabricating these ceramic membranes, such as Nascon and others, for a variety of different applications. So one fabrication technique we've been very excited about was one that's actually developed by my colleague at Yale, Liangbing Hu, where you take your precursor powder and you press it into a pellet, and he's developed a ultra-fast high-temperature sintering process that does go up to high temperature, but only for less than 20 seconds, so in the order of 10 seconds or so, before you actually get your final membrane. So this could be, in principle, a way of getting, of doing high throughput and somewhat low-cost fabrication of these membranes at high quality. And we're interested in taking these membranes and then putting them, again, in electrochemical systems that would be used for things like CO2 removal from seawater, or even nitrogen removal from wastewater as a way of generating fertilizer. Okay, so this was really all I prepared. The goal was to give you a snapshot of the various activities going on in my group and their industrial or potential industrial applications. So on the research side, to summarize, we're very interested in designing organic molecules that can be used as energy carriers in flow batteries, and also proton transfer agents for carbon capture. And then secondly, we've been deploying ceramic membranes in electrochemical cells, both for energy storage and also for a variety of selective ion separation processes. And the goal, one of the goals of our group is to take a lot of this fundamental insight and to show that it can be used in, or find ways to deploy it in storage of renewable electricity, energy arbitrage or electricity arbitrage on the grid, provision of low-cost CO2 as a feedstock or as a product, extraction of nitrogen from wastewater, desalination, etc. And the hope is that a lot of the potential applications involved here can feed back into our research, so that we are doing things that are sort of relevant to making the world a better place. So with that, I'll acknowledge all the folks who've been involved in this work. There's been a number of people from my group, and the names of those who've been involved, most of what I've showed up down here. I have several collaborators from within Yale, but also across different universities in the US, and then funding agencies on the bottom. So thank you very much for your attention, and I'll be happy to take any questions.
Thank you very much, David. Excellent presentation. For those who haven't seen our previous webinar, Professor Liang Hu was our first webinar speaker, and he mentioned about the joule heating that Professor Kwabi just mentioned. So I encourage you to go to KCITY website. There's more detailed discussion about this shock heating process, including both joule heating and plasma for various material synthesis. I'm also collaborating with Bing Hu for the synthesis of some of the high entropy materials. Any questions from the audience? David, don't get disappointed. It was pretty common so far, but I would be happy if there's any new, anyone brave to ask a question. You're welcome to question in Korean.
Maybe if there any question from Korean side, you can ask in Korean as well, so that Dr. Kim can translate for Kwabi. Or yeah.
In the meantime, David, I will just ask one question. It seems like this redox flow batteries, may fail. Maybe one of the reasons they fail is because of this crossover.
Yeah.
But once it gets crossover, is there any way that you can regenerate the electrolyte?
Yes. So let me go back here. It's a great question, and the short answer is that there are a number of ways to potentially recover crossover species, but it strongly depends on the molecule in question. So
it sounds like it's going to be easier if you're working on the organics than vanadium, right?
that's right. So for example, if you're working with like a sulfur manganese, for example, let's say, and you have dissolved sulfide on one side, but it crosses over and then it ends up either as, well, let's say like a completely reduced sulfide, and then you get precipitation.
Right.
In principle, you can try to go about, sorry, let me see if I can find the right slide here, because all the other strategies are listed here. So there you go. So in principle, if you can see my cursor, you can actually do some recovering, depending on the species that's crossover. If it precipitates and is easily separable from the other species, then over time, after you get some capacity fade, you can do that separation and then sort of go back and restart. There are some chemistries for which recovery will be very challenging, because when the crossover occurs, there's perhaps a destructive reaction with the other molecule that's already present in, say, the negalite or the posilite, and then there's really there's no hope, because you have some sort of irreversible reaction. So it really depends on the chemistry you're working with. And the reason we're interested in NASCON is that if you're able to perfectly separate the electrolytes, then then there's really no crossover to begin with, and you don't have to worry about recovery.
Right.
But it's a good question.
Yeah. I wonder if there's any expert in the flow batteries among the audience, but if not, it's okay. I hope if you have colleagues who are in this area, please forward this link to your colleague so that word can spread. If there's no question, it's already 9:50 in Korea. So I think I'm going to conclude the recording.